Hello, my name is Joe Archer, and today I want to talk about transoceanic rail. While it has been proposed and may be being built in Norway, the way that it is being built is neither cheap nor logical. It turns out that a case can be made for building a submerged rail quite cheaply, such that it is actually an economically viable concept. So how could transoceanic rail be built in a way that could actually pay for itself? Well, the simple answer is by pumping out a continuous concrete tube that is suspended with buoys a few hundred feet deep and possibly cabled to the ocean floor at miles intervals. The cost of such a tube is so low that it is hard to believe. If the tube is 20 feet inside diameter, with a wall thickness of 2 feet, it would only require about 5 yards per linear foot. This equates to about $5 billion in concrete at raw material cost. A reasonable estimate of reinforcing cable is a similar cost. You might estimate a possible billion for anchors and another billion for buoys, and it comes in at 10 billion for an evacuated two-way New York to London tube. These low costs are accommodated by the fact that the tube construction is nothing more than a continuous pouring operation, and the buoys can be attached at shore, thereby eliminating any deep sea operating costs. Also, the reinforcing cables can be put in tension, so that the tube itself offers almost no deflection even at considerable lengths. The actual labor cost of such a tube would only be a rounding error in comparison to the very low cost of the raw materials themselves. While the costs are minimal, there are some technical issues that need to be clarified. A floating tube must accommodate North Atlantic swells and the weight of a passing train. The simplest way to address swells is to use more and smaller buoys, and possibly elastic support cables. This way the action of one buoy is minimized because of its smaller size and because of the elastic action of the support. As for a passing train within the tube, the weight of a 500-foot train traveling at Mach 1 would only act on any point in the rail for half a second, so that the deflection of the tube due to the train weight would be quite small, as it is acting against a longer section of rail that has a great deal of mass and thus inertia. Another technical point is the ocean currents. If ocean floor anchors are used, they must be frequent enough to accommodate even a slight deflection of the tube. And because they add significantly to the cost, it would be far better if the cables in the tube were strong enough to allow just end-point anchoring. If the tube is anchored only at the ends, the tube would sag in the direction of any ocean cross-flow current. This means the best course would be through the Arctic Ocean, as ocean currents are minimized, as well as being in the direction of the tube. This idea of running a New York to London tube through the Arctic offers other advantages, such as eliminating the need for buoy supports or the disturbance of storms. Because shipping traffic does not use the Arctic Ocean, the case can be made for floating the tube across the Arctic Ocean. However, this is a little problematic because of ice flow issues. It may not be possible, but if it were, it could serve a dual purpose of both a rail and a road between the continents. But it is questionable who such a road would serve, or whether it would ever be driven. Now, of course, this hasn't addressed the functional cost. Clearly, using the conventional implementation of magnetic levitation would make the concept impractically expensive. However, because conductors are added to the tube during fabrication, a conducting rail or just a cable can be added specifically for the purpose of providing an electric field along the tube. This field can then be used to support a conveyance lined with magnets, electro or otherwise. A notable thing about this approach is that because the tube is laser straight, the conveyance can be supported at millimeters from the wire to reduce electricity costs and improve performance. The power from the tube cables could power a conveyance to generate the high magnetic field needed to levitate a conveyance. Only this form of mag-lev support is affordable. However, if this method weren't practical, it is also possible to use larger, lightweight wheels to support a conveyance, as the tube is sufficiently perfect and track debris is not an issue. For a 10-foot diameter conveyance, 10-foot wheels could be used so that even at Mach 5 speeds, the wheel would only spin at 150 revolutions per second. In that flywheels have achieved 6 times that, it doesn't seem implausible. Regardless, much slower speeds are certainly possible, such that conventional wheeled conveyances can be used. Even if such a train were limited to a few hundred miles per hour, it would operate in a vacuum and use so little energy that it could easily compete with air travel absent any CO2 production. However, it must be said here that any inclination to settle for a lower speed conveyance should be strongly dissuaded. It must be emphasized that an evacuated tube of such straightness and rigidity offers an Olympic opportunity that cannot be denied. Clearly, if this described mag-lev on the cheap system is feasible, there really isn't any reason an evacuated rail cannot accommodate at least Mach 6, if not Mach 15 and 20 and more. And to shoot for anything but the most achievable speeds is not worthy of us. But besides providing affordable magnetic levitation, this rail can transfer electric power to a destination. In addition to conveying power using the rail itself, all the reinforcing cables in the walls could be used also. While a 3,500-mile transfer of power may only be valuable to a desperate party, the far lower total resistance to current flow using a 1 to 300 cables would greatly reduce line losses, and 100 more cables can be added quite affordably. In truth, if one could line up a multi-year contract for electricity sales before construction, they could easily finance as many extra cables as possible. Whereas a workable tube might have just a few dozen cables, a pre-sold electric conveyance tube having hundreds of cables would be a thing of beauty, both because of its low line losses and because such a tube would be so strong. In almost all likelihood, a tube could pay for itself just by transferring power within the tube itself. But on a side note, the conveyances can be shielded from the EMF field within the tube due to the flow of electricity. This is an important point, as it is probably not in a person's interest to be subjected to such a field. Another potential financial incentive offered by a formed tube is the ability to provide material transfer across nations. Simply by forming a tube in the extra cross section of a tube not used by the rail, it would be possible to generate revenue moving fuel or even water. Because this feature adds no cost to speak of, it has to be factored in the financial viability of an extruded concrete tube. In a 20-foot diameter tube, several 4-foot diameter tubes capable of moving millions of gallons a day could generate a considerable amount of income, and could probably pay for the tube just for this revenue. The final technical point is speed of construction. As all projects requiring capitalization are conditionally affordable in how fast they can begin generating revenue, if a single extrusion was fabricated, even the most amazing productivity would require a decade to complete. However, it would be a simple thing to set up 10 extrusion units and then connect the tubes together so that the entire project could be completed in as little as a year. It would only add marginally to the cost while saving far more in both time and finance. The only real issue as to the viability of a transatlantic oceanic rail is the capitalization cost and potential payback schedule. So let us assume a completed cost of $20 billion, which is twice that of the estimated lowest cost of fabrication. A 5% annual interest and principal payments, the rail would need to make $1 billion a year in profit. If each train is 500 feet long and 10 feet wide, you might reasonably estimate 200 people per train. If you define a 15-minute separation operating 6,000 hours a year, you could come up with nearly 5 million two-way round-trip tickets. If you charge $500 per round trip, this generates $2.5 billion per year in revenue. Since you're not paying for fuel, this leaves you about $1.5 billion a year for ticketing, service, and maintenance fees. As a first approximation, it is clearly possible that such a tube could actually pay for itself if not prove far more sound an investment than most. However, this estimate of 15-minute separation between trains is far greater than is really necessary. Regardless of what speed your conveyances are limited to, you could probably reliably operate with as little as 1 minute separations between cars, as computers would be able to stop all cars at the same instant and easily prevent any collisions. In all honesty, a tube like this could reasonably handle 15 times the revenue calculated above, so that the operating and payback margins would be so great that it could pay for itself in 1 year. This means that even if such a rail costs more by a factor of 10, it could still be affordable if there were enough people interested in traveling to London or New York. However, even if these numbers are optimistically profitable, such that such a tube were not cost effective, there's something to be said for building a tube just because we can. From the analysis presented here, it is at least a conceptually feasible endeavor, and it is certainly conceivable that evacuated rail is a way to move people much faster and using much less energy. But another advantage is that the application of continuous concrete pouring for transmarine transit has thousands, if not millions, of opportunities on a planet that is two-thirds water. Every place that a ferry is in operation, a submerged tube would be far better and cheaper, and therefore many places that won't support a ferry can have the convenience and service of a submerged tube. And because of their extremely low cost, submerged concrete tubes would be of fantastic service to poor island nations. Another great thing about such a tube is that it would require so little, if any, maintenance. But maintenance aside, what may be the most attractive thing about submerged concrete tubes is their impact on the environment. Aside from not presenting an eyesore, submerged tubes would create artificial reefs that would foster marine life in the open oceans. Of course, this would have to be accommodated for in the design of the buoys, but the potential upside from an environmental point of view is hard to estimate, but would almost certainly be quite a boon for fish populations. So there you have it. This is my argument for how and why a submerged concrete tube should be built, not just for a New York to London transit, but for 1,001 connections worldwide. We no longer need to spend billions on huge cable spans because we can now just squirt out a concrete tube like crazy for a penny on the dollar. And we might even be able to eliminate the need for slow and energy demanding ship transport in a natural evolution to smarter, faster, and cheaper transport systems.